Okay, so the plan for today is to finish up the last problem from worksheet 15 that we didn't get to last time, and then work on worksheet 16, which deals with phase plane equations and equilibrium. So we've been introduced to these things a little bit. And I just want to let you know that starting next week, we're going to be using methods that involve quite a bit of linear algebra. So the reading quiz for Monday will just be a review of linear algebra, matrix multiplication mainly. So if it's been a while, there'll be an example video that I put up. But if you're taking 3191, hopefully you're expert matrix multipliers. And we'll kind of use some material from eigenvalues and eigenvectors next week. So if you've taken 3191, you've seen this. If you're currently taking 3191, I checked in with those instructors. You'll see eigenvalues, eigenvectors in 2 weeks or so. So we'll be doing some stuff that you'll see shortly in linear algebra. But today we're going to be working with phase plane equations and mainly using techniques of solving first order differential equations from earlier this semester. So any questions before I get started? Okay, so I just want to back up. This was the last problem on the worksheet from last time that we didn't quite get to. And so recall we were working with null clines last time, X and Y null clines. So here we're dealing with, the setting here is we're dealing with two interacting populations, we'll say rabbits and sheep. And so these are not typically predator-prey relationships. I don't think rabbits would try and eat sheep or vice versa, but they do have a competitive relationship in the sense that they eat the same food. So we have different dynamics from the rabbits and the foxes here. And so I just want to be clear that, right, we're thinking about R as the Y and S as the X here. So let's just kind of review. And for us, this really means R null clines. But recall from last time that these occur when the equation for Y, or in this case R, is 0. And so when that happens, recall that dr ds okay, assuming that the SDT is not 0, we would get the RDS is equal to 0 over some non-zero number, and that would give us 0. So in other words, these are going to be vectors in the plane that have no slope. They only are horizontal. So they're going to go this way or that way. So that would mean here's an R null cline right here. And here's another one over here. So any line where all of the vectors are horizontal, these would be the Y or R null clines in this sense. Any questions about that?
Just for clarity, that pound symbol, that would be ds dt technically?
Yeah.
Okay, then all good.
Yeah, and what we're also assuming here, we're going to say dy dt is 0, and it's kind of implied here that the s dt is not 0, because if they're both 0, then that's not a null cline, that's an equilibrium. Yeah. Any other questions? So last time we talked about when we had equations, how to find them and how to determine the directions of these things. And so this time it's kind of the reverse. Here's a bunch of null clines. How can we identify what is what in this picture? And conversely, when we're talking about X null clines, this is equivalent to, in this case, S null clines. And it's the flip of that. So here we've got the S dx dt, which is the S dt in this case, is 0. And we're going to assume that the other derivative is not 0, or else again, we would be at an equilibrium. And yeah, and so these vectors in the phase plane, since we would be dividing by 0, these are going to be vectors in the phase plane that are undefined. And what that means is they're going to point directly up or directly down. So that would be this line right here, and this line right here. Any questions? So let's see. So that's part A and part B. So up here was A, and down here is B. And then if we want to find the equilibrium, which is what C is asking, we don't have equations here to find them. So we just have this picture. How do we identify equilibrium in this sort of vector field here?
You can look at where two different null clines intersect.
That's right. So for example, here's an equilibrium at 0, 0. And we have another equilibrium right here, where the R value is not 0. Excuse me, it's the other way around. We've got S is equal to 0 here, and R is some non-zero thing over there. And how many other equilibrium do we have?
2.
Yeah, we've got another one over here and another one over here. We've got a total of 4 equilibrium in this system. And just be careful that this point over here is not in equilibrium because it's an intersection of 2 y null clines. And this point over here is also not in equilibrium because it's an intersection of 2 x null clines. Okay, questions about that? Okay, so part D is now saying these null clines divide the phase plane up into 4 regions. I'll just number them here. So we'll say that's 1. This is region 2. This is region 3, and we'll call this region 4. And remember that inside of each of these regions, the vectors are going to have the same general direction. So it kind of divides the plane up into regions where the vectors generally are pointing like up and to the left, down and to the right, or whatever. So to determine which way it's going to go, we can see that over here, we've got vectors going up, and we've got vectors going to the right. So we can kind of say this is going up, should be going to the right. So altogether, our vectors are going to look like up and to the right. Okay, versus over here, things are going up and to the left now. And over here, we're going down and to the left. And then way out over here, we are going down because of these vectors over here, and we're going to the right because of those vectors over there, or excuse me, the left. So over here, the vectors are looking like that. So we kind of just look at the 2 directions that are being bounded by all of these null clines, and then we say the direction in this area is going to take into account both of those things. And it's not going to change direction anywhere in there because the only place where it might change directions is when we cross over a null cline. And so just so it's clear, if you haven't taken a look at the homework just yet, you've got a question on the homework that's going to ask you to kind of go through some of these things, but you'll be given the system and then have to sketch the null lines and then have to do some analysis like this. And so ultimately what we might be interested in is like, what is going to be the long-term behavior of these interacting populations? Are the rabbits population going to increase forever and the sheep die off, or vice versa? So often we're not even interested too much in like individual solutions, but what's going to happen in the long run. And so if we look at this equilibrium over here, and we start at a point close to it, but not exactly at it, what's going to happen as time goes on? Is the solution going to head back towards this equilibrium, or is it going to head away from the equilibrium?
It's going to head away.
Yeah, it's going to head away, right? Because if we start here, we go up and to the right, which actually moves us in the direction towards this one over here. If I start over here, we go up towards this equilibrium, so we're moving away. If I start over here, we move over towards this equilibrium, so we're moving away. So this equilibrium, we would say, is really unstable, since any solution that's near it is going to move away from it. This one over here, we can see that if we start near this equilibrium, we go here, we start over here, it goes in. All of these arrows are pointing in towards that equilibrium. So this one over here would be a very stable equilibrium. And this one over here, we have an example where in some cases, we're moving in towards the equilibrium. In other cases, we're moving away from the equilibrium. So here's a case where in some directions, we would head back to this equilibrium. With other initial conditions close to this, we wouldn't. So we would call this equilibrium over here a saddle. And for the same reason, this one over here is also a saddle. And okay, so any questions about that? And practically speaking, you should be thinking, okay, we've got rabbits and sheep in this ecosystem interacting with each other. Why does it make sense that the equilibrium are behaving this way? Well, if we start with like 2 rabbits and 2 sheep, something close to 0, we're going to approach this equilibrium over here. However, if we started with no rabbits and just sheep, then we're going to remain with no rabbits, and we're going to approach this equilibrium, this limiting capacity for sheep. But if we do include a little bit of rabbit over here, then that's when we approach this equilibrium over here. So this is kind of the equilibrium that if initially you start with some rabbits and you start with some sheep, then as time goes on, we're going to approach this rabbit population and this sheep population over here. Okay, any questions?
Saddles are still considered unstable equilibriums, right? Are they like a subset of it?
Sorry?
Are saddles considered like subsets of unstable equilibriums?
Depends. We use different terminology for this. So some people might call this semi-stable, and some people will just call this unstable. For me, I want to make this distinction between like totally unstable, and this is a different behavior. So I don't like calling this unstable. So for us, let's call them saddle points or semi-stable equilibrium. Calling them unstable is like the glass half empty. I like to think about the glass being half full, and there are some directions where it would be stable. Any other questions? Okay, so then that's a wrap on null clients and vector fields. And I want to now talk about phase plane equations and equilibrium, worksheet 16. And we're basically still in section 3.1 in the textbook. So the textbook crams so much stuff into 3.1. So I did put some supplemental notes that kind of focus just on phase plane equations. So there's some additional stuff to read for that, just like there's a separate set of notes for null clients. So this was the example in the video, and on the reading quiz basically asked you to do something similar. So for those that might not have watched the video, let's say we've got this system of differential equations, dx dt 7y dy dt is minus 2x. And let me just say, what we're hoping to get when we solve this would be to get two different solutions. Here's how x depends with time. Here's how y depends on time. Here's how the rabbits are going to change with time. Here's how the sheep are going to change with time. So let me just say, when we're kind of solving these today, we're finding solutions of a different sort of variety. We're looking at how these two variables, x and y, interact with each other. And we'll get to this next week. So for now, I want to just think about things in the phase plane and how we can find phase plane equations. So first bit of information is how do we find the phase plane equation? Well, it follows from the chain rule, and the phase plane equation would be an equation for how does the slope of y depend on x? And we can write this equation by taking the equation for dy dt and then dividing by the equation for dx dt on the bottom. So in this case, if we've got 7y minus 2x, then we would take dy dt, which is minus 2x on top, and put 7y, which is dx dt on the bottom. So this would be what we call the phase plane equation. Any questions how we can come up with those? And so after we find the phase plane equation, it's a first order Diffie-Q. So for us, if that equation happens to be separable or linear, then we know how to solve these. We might get some that we don't have techniques to solve just yet. Okay. So in this case, it is separable. So I'll kind of skip the details of the calculation, but we could separate it over here. We can integrate both sides. And then the best we can do is get an implicit solution over here. So at this point, it kind of falls back, to material from earlier in this semester. And then if we want to sketch this in the phase plane, then we could take this equation over here and we want to plot it down below. And you might look at this and think that, yes, if I take away that, what would that equation, what would those equations look like in the plane? X squared plus y squared is c.
A circle?
Yeah, so those would be a bunch of circles with radii square root of c. When I put this 7/2 in front of it, it kind of warps the circles a little bit, and we wind up getting a bunch of ellipses like this. And so if you've taken Calc 3, vector calculus, and you've done some work like a contour diagram, this is exactly what we have here. So this is a contour diagram for the system if we were to draw it in XYT space. So when you draw these, a couple of things you want to include. You want to include like, what does the shape of the curve look like? Different curves should correspond to different values of C. So you might want to, you should label your curves with what value of the constant does it correspond to. And then the last thing that you definitely want to pay attention to is finding the direction that you move along these curves. So let's kind of consider the right here. Like if I were to start on this curve at what seems to be something that is, you know, close to 2,0. But I'll just say the x value is non-zero and the y value is 0. How could I figure out what direction we're moving at that point? Right, there's pretty much two options, up or, excuse me, yeah, so it's going to be like up and to the left, down and to the right.
Plug that value back into your derivative. To see
Yeah, so we can plug it back
positive or
into
negative.
either one or both of these equations to see where we're going. And if you're looking at this one, because we're at this point where we're changing horizontal direction, right? The options are we're going to either be moving up or we're going to be moving down. No matter what, we can see that we're going to be moving to the left once we start moving. So to figure out whether it's up or down, we can check dy dt. And over here, this x value is positive. So we can see that at this point, dy dt is negative. And that comes again from plugging a positive value for x into this equation, we would get a negative value for dy dt. So that tells me that's the direction that we must be moving. And that analysis is the same on each of these curves. So all of these motions are moving clockwise along these curves. So that's really important when you're sketching these. I just want you to be aware that it's not just the curve itself, but also we need to indicate time somehow on this graph. And the way we do that is by putting arrows in. If we were to hit play, what direction would we move as time goes on? Okay, so any questions about phase plane equations? Okay, so next up would be equilibrium, and we've kind of chatted about this already. So pretty much we've got all the material that we're going to be working on today discussed. So when we find equilibrium, these are going to be values for x and y where the x dt and dy dt are both equal to 0 simultaneously. So in other words, when we're finding equilibrium, we're going to need to solve a system. Which oftentimes is going to be non-linear system. So maybe let's take a look at B, and I'll leave you to think about A in a second. Yeah, let's do it the other way. Let's start with A, and then maybe I'll help you think about B. So here's A, and we want to find equilibrium to this. So we would want to kind of first set both equations equal to 0. And so now we want to find values for x and y that are going to make both of those equations 0. Okay, and so then becomes algebra. We might substitute, factor, eliminate, etc. And we want to solve for pairs x, y. So we're not just solving for x or y. So you want to find values for x and y that make both of those equations 0 at the same time. So any thoughts how we could start this one?
Since there's no y term in the second one, why don't we just solve for x and then put it into the first?
Yeah, so using the equation for dy dt, that would give us, right, x is minus 2. So this doesn't tell me that any point that has x equals minus 2 is a solution, because I also need to check to make sure excuse me, in this case, dx dt is also 0. So what this tells me is that any equilibrium must have x equals minus 2, but keep in mind, this is different than saying all points that have x equals minus 2 are equilibrium. And so to find the conditions on y, we can substitute this into the other equation. So the equation for dx dt was 2 times x minus y plus 8 is equal to 0. And again, that comes from this equation up here, and we're plugging in minus 2 for x. And I'm solving for this one. What would we get? So that would be minus 4 plus 4. I think that just would give us y is 4 for the condition on y. So in this case, we had one equilibrium. It's very possible, as we saw in the first RS no climb problem, that we could have more than one no climb, or excuse me, more than one equilibrium. And in some cases, you might have an infinite number of equilibriums. So don't just expect to get one unique solution. Any questions? Okay, I will, I'm gonna set up some breakout groups just for you to work on part B. And the task is to find equilibrium solutions. So that's it, not the phase plane equation. We're not solving the phase plane equation, just identifying equilibrium by solving this system, and you should find more than one equilibrium in this case. So any questions what to do? Okay, so I set up some breakout rooms. Maybe we'll take about 10 minutes to work on this. If you happen to get done with it in your groups, you can move on to question 4 if you like. But please, before you move on, to the next part, just make sure everybody in your group is with you and figured out part B together.